Hi, so this video is going to be about collecting like terms. So before we get to the process of collecting like terms, we need to ensure that we understand what like terms are. So from the vocabulary list that you worked on last day, you would have discovered that like terms are terms that have the same variables to the same powers. So you'll often hear it said that they're the same variable form, meaning that term has the same letters and all the same exponents on the same letters. And if that criteria is fit, then those are considered like terms. So in the example here that we have in the box that you probably would have copied down into your vocabulary list, we see that 4x and negative 3x are like terms, remembering that the symbol goes with the term, so that negative is part of the negative 3x term. And then 4x and 3y are not like terms because they don't have the same variables. And xy and 3y are also not like terms, again, for the same reason that they don't have the same variable form in them. So when you have an expression or an equation that has like terms in it, one way to make that expression or equation simpler is to collect the like terms. Now, the important thing to remember when you're collecting like terms is that the variables themselves do not change. It is just the quantity of them that changes. So the coefficient changes, but the variables themselves stay the same. You're just collecting up and sort of sorting things that are the same. So putting them into piles of the same thing, more or less. So if we look at these examples down here, it says, where possible, simplify by collecting like terms. So in the first one, we have 3x and 2x. Those are like terms because they have the same variable form. So imagine you have 3, you pick up 2 more, now you have 5x. So the variable itself doesn't change, just the quantity of the variable changes. And so in B, we have 7a minus 3a. So again, we do have like terms because we have the same variable form. We had 7, we lost 3, now we have 4. So again, variable itself doesn't change, just how many of them you have changes. So C, we have negative 2x plus 3 minus x. Now, some students will find it helpful to kind of, in the beginning, use colors or use some sort of a coding system to identify the like terms. So in the first two examples, there were only 2 terms. They either were or were not like, and we put them together. But now we have 3 terms that may or may not be like. So some students would find it helpful to say, okay, here's a term with an x in it, and then sort of go down the list, oh, here's another term with an x in it. And so they understand which terms are getting put together. Now, the other thing that you need to recognize is that in front of this x term, there is an unwritten 1. That x has a coefficient of negative 1, so you need to factor that in when you are collecting your like terms. So if we tackle the x terms first, we have negative 2 minus another 1. So we are down to negative 3x, and then my positive 3 has nothing else to collect with it, so it just kind of hangs around for the ride. So part D, we have 3bc plus bc. And again, remembering that in front of that second bc, there is an unwritten coefficient of 1 that we need to consider when we are collecting our like terms. So we had 3bc, we added 1 more to our collection, so now we have 4bc. Again, variables are not changing. Variables will only change when you multiply, which is the next section, but not today. When we're collecting like terms, we are adding and subtracting terms that are considered like. The variables themselves do not change, only the coefficient. So then we get to E. We have 2x minus x squared. Now hang on a minute. Those are not like terms. This term, this 2x, the variable form is just x to an unwritten power of 1. The variable form of the second term is x squared. If the powers on those variables are not the same, they are not like terms, and therefore cannot be simplified any more than they already are. So you might write something like, cannot be simplified. That is as simple as you can make that expression. Okay, let's look at a couple more examples. So again, we're getting into longer, I suppose is a way of saying it, longer expressions that have more terms in play. So again, some students find it helpful to color code in the beginning when you're just getting used to this concept. So we have this first term, which is a constant term. So we're looking for other constant terms, and we see that one that exists. So we have 2 minus 3, which gets us down to -1. And then use a different color. We have 3a minus 2a. So again, remembering that the symbol goes with the term. So we have positive 3a minus 2a. So 3 minus 2 gives us 1. When we have a coefficient of 1, we don't need to write the coefficient of 1. We can just write plus a. If you were to write -1 plus 1a, it's not wrong. It's just a more accepted way of writing it, I suppose, is to not write the coefficient of 1. And then in part B here, again, we can color code things. So we have an x squared term to start, follow through our expression. We see another x term or x squared term there at the end. So again, remembering that unwritten coefficient of 1. So we have 1x squared minus 2x squared. So 1 minus 2 gives me -1. Again, I don't need to write the 1. I can just write negative x squared. And then again, move on to the next kind of term. So we have -2x plus 3x. So -2 plus 3 gives me +1. So again, I don't need to write the coefficient of 1. I can just write plus x. And again, if you were to write -1x squared plus 1x, it's not wrong. It's just, I don't know. I guess you just need to get out of the habit of writing that coefficient of 1 and just understand that without the coefficient of 1, there is still a 1 that exists there. Okay, so that's everything you need to know about collecting like terms. Just to review quickly, you need to make sure that you have like terms, same variables, same powers. And then if you have that established, they can be collected up and just sort of piled into the same kind of category to then make your overall expression shorter and therefore in math terms simpler. So the instruction you'll often be given in this is to simplify. Make it simpler by collecting up everything that is the same. Okay, thanks very much.